Okay, so now let's take a look at number 4. Number 4 is also a chapter 8 problem, very similar to the one we did yesterday with the shot put. Okay, so this one is a chapter 8 question. Alright, so for this one it says, if you hold your arm outstretched with the palm, or with your palm upwards, it says the force to keep your arm from falling comes from your deltoid muscle. Okay, so basically I have my arm out like this, right? It's in equilibrium because my arm isn't accelerating clockwise, counterclockwise. It's not accelerating up, down, right, or left, right? So the net force acting on my arm is 0, and my net torque acting on my arm is 0. Okay. So first off, let me go ahead and draw that here. So it says that the center of gravity of the arm is right here. So this is where the weight of the arm is going to be acting, the mg. And it says that that is, if I draw my pivot point here, it says that that is 38 centimeters away from my pivot point, the mg. And then I also have the force that the deltoid muscle is exerting, but it's exerting it at an angle, something like this. And it tells me that that angle is 15 degrees, and this is the force that the deltoid muscle is exerting. Okay. And that force is exerted 17 centimeters from the pivot point. This one's actually a homework question from chapter 8, so I want to do this one. So, first things first. Would you agree with me that this guy is already perpendicular? The mg is already perpendicular to the arm. So it's going to generate maximum torque on that arm, right? About this pivot point. Does everybody agree? This deltoid force, though, is not perpendicular. Does everybody agree that it is not perpendicular? So it is going to generate a torque because it at least has a component that is perpendicular, right? But it's not going to generate the maximum torque that it can, right? And even mg has an advantage from two perspectives. First of all, it has an advantage over FD because it's perpendicular, and FD is not. Would you agree? Also, it has the advantage because it's further away. So that deltoid muscle force better be a very large force in order to be able to cancel out the torque generated by the weight of the arm. Because that deltoid force is actually not perpendicular. And also it's closer, so it's not it doesn't have that advantage that this one has because it's further away. So this deltoid force is going to be much larger than the weight because of that, because it has to balance out the torque generated by this weight.
Is that 17 centimeters?
That's 17 centimeters, yeah. Okay, so now what I'm going to do first is I'm going to go ahead and break this up into a component that's perpendicular. Would you agree with me that if this angle is 15, that this angle would have to be, what, 75, right? So this angle would be 75 degrees. And I'm going to go ahead and erase the deltoid force here, and I'm just going to put it right here. I'm just going to relocate it. And I'm going to draw the other component just so that you can visualize it. But I only really need one of them. Does everybody agree that I only need this one? Yeah. And is that adjacent or is it perpendicular?
Adjacent.
Adjacent. So that's going to be cosine, FD cosine of 75 degrees. And we're almost done, basically. So from here, all we have to say is, well, we want to find the deltoid force. So we're going to sum torques about 0.0, and we're going to set it to 0. Why are we summing torques and setting it to 0? It's not accelerating. It's in equilibrium. It's not accelerating clockwise. It's not accelerating counterclockwise. Yep.
So why is your mg positive, not negative?
That's, again, you can put it there if you want. You don't have to. In the equation, it better be negative. But in the free body diagram, if you want to put it in there, you can. If not, then you don't have to. Yeah. Okay. So here we go. So what we're going to do is first, we're going to calculate the torque generated by this guy. So I'll go over here. I'll call that torque 1. So torque 1 is going to be F perpendicular, which is my FD, cosine of 75, multiplied by radius, or distance to the pivot point, which is 17 centimeters. But I'm going to convert that to meters, so 0.17. Okay. Now, will that be a clockwise torque or counterclockwise? Let's look. I'm going to hold my pencil right there, parallel to the arm, holding it at the pivot point. I'm going to push it up. Which way is it rotating? Counterclockwise. Excellent. So that's going to be plus. And we're almost there. So this torque, I'll call that torque 2. That's going to be F perpendicular. Do I include the negative sign for the mg even though it's down in the torque calculation? Or do I only include a negative in torque if it's clockwise? Only if it's clockwise. Okay, so even though this force is down, doesn't mean that you'll include the negative. At the end, you'll have to think, is it clockwise or counterclockwise? So we're just going to make it mg for now. That's my F perpendicular. I don't need to break it up, right? Because it's already perpendicular.
You already see it, then you can put it.
If you already see it, you can put it in, yeah. Now, the distance. How far is that from the pivot point?
38
0.38.
centimeters.
Now, that one's going to be a clockwise torque, because take a look. I'm going to hold it right here. I'm going to push down. Which way am I rotating? Clockwise. And now, all we really have to do is sum those up and set it to what? 0, and we're done. That's it. So it's going to be FD, cosine 75, times 0.17, minus mg. They already told us the mass of the arm, so I'm going to go ahead and put it in. mg times 0.38 is equal to 0. And all you would have to do now at this point is solve for your FD, which there's only one variable, so you can do that. Okay, so does everybody see how we got this? Is everybody comfortable? Okay, so that would be the calculation for FD. That's it. Okay, so let me show you some of the conceptual questions now.
For part B.
Oh, there's a part B.
Yes.
So it says, by what factor does this force exceed the weight of the arm? Okay, so what you would need to do at that point is you would need to first calculate what FD is, right? And then what you do then is you do a ratio. If you want to compare two numbers, you have to do a ratio, right? Like for example, if you want to compare the number 4 to the number 2, you do 4 divided by 2 and you get 2. So 4 is 2 times larger than 2.
Yeah.
If you want to compare 12 to 4, you do 12 divided by 4, you get 3, which means that 12 is 3 times larger than 4, right? So if you want to compare the deltoid force to the weight of the arm, you're going to calculate a ratio between the deltoid force and the weight of the arm, which is mg. And then you're going to get a ratio. Let's say, after we do the calculation, we end up with 3.5. What does that mean? That means that the deltoid force was 3.5 times higher than the weight of the arm. So that's what it would be.
Oh, so you would do like 338, which you have here.
Yeah, so the deltoid force after you solve it is 338, right?
Yeah.
Okay, so let me just go ahead and put that there. So deltoid force after you solve is 338 newtons. Okay, so now what you would do is you would do 338, which is your deltoid force, and then you're going to divide by the weight of the arm. Now the weight of the arm would be 4 times 9.8, the mass of the arm times acceleration of gravity, mg. And then that would give you the ratio, and what did I get for that? 8.6. Which means that the deltoid force had to be 8.6 times higher than the weight of the arm, which is what we talked about conceptually earlier, because the weight of the arm had the advantage over the deltoid force, because it was further away and it was perpendicular. The deltoid force was applied closer to the pivot, so it already didn't have the advantage. It was closer, so it doesn't generate as much torque. And not only that, it wasn't even perpendicular. So that deltoid force has to be much larger in order to generate equal amount of torque, but in the opposite direction, that the gravitational force does. That's why it's so large.